Welcome, everyone. If you know anything about LLMs, agentic AI, deep learning, machine learning, generative AI, these are all under the bucket of artificial intelligence. You are here because you want to learn about where all of this began, how we got to today's ChatGPT, Claude, and all these general purposes. So let's get started. By way of introduction, my name is Hessie Jones. This is my colleague, Saurab Tripathi, and we'll be presenting today. So I guess I wear a couple of hats. I have worked in data privacy and AI for about 8 years. I worked in startups in technologies that did contextualization, profiling solutions, as well as remediation for AI risks. I advocate for human-centered design, but I'm also a program manager here at Altitude Accelerator, where we develop programs to actually support startups as they scale. I'm also a writer, I'm a journalist. I talk to many wonderful leaders, researchers, and entrepreneurs who have a lot to share as technology progresses in AI. So I'm going to go to Saurab and let him introduce himself before we get started.
Sure. Thank you. Hey, I'm Saurab. I'm a machine learning engineer, currently working with Samsara. I've been working in this space, the AI ML space, for about 10 years now. And yeah, over the course of my experience, I've worked on the vision problems, natural language, machine learning, ML ops, off lately a lot on the multimodal AI or edge AI. Glad to be here.
Okay, so we're going to cover today some of the origins of AI from the early 50s, how we evolved to machine learning, neural networks, generative AI. So across this presentation, I am going to cover generally what works within these systems, and Saurab will take you through what's happening underneath the hood. Okay, let's get started. John McCarthy was a young professor at Dartmouth, and he was a pioneering computer scientist. He is credited with actually coining the term artificial intelligence in 1955. The next year, there was a Dartmouth workshop, and they aimed to explore how machines could actually simulate human intelligence, solve problems using language, and how they could improve themselves. So he introduced the term artificial intelligence as a proposal for the first major conference dedicated to AI. And his peers actually liked less flashy terms. They liked complex information processing or operations research. Can you imagine if that actually replaced AI today? So the term helped to unify these diverse researchers under this common banner that effectively launched AI as a distinct field within computer science. So it became this guiding ideology and framing for the work, trying to recreate human intelligence within machines. It remains a broad term. So when people say AI, they may mean current systems, but for the most part, it means many, many things. So scientists have poured their own meanings into what AI is, but generally it is the ability of a computer or computer-enabled systems to process information in a way that's similar to the way humans process information, how we make decisions, and how we solve problems. So there are two main philosophical frameworks when it comes to artificial intelligence. Earlier on, there were symbolists who believed that intelligence comes from knowledge. So these are experts. So they required building knowledge systems and using that for systems to be able to learn from them so that they can actually help people. But the one thing about these, find out later on, is that the specific rules were very tight and less scalable. Connectionists actually believe that intelligence comes from the learning ability. So recreating it to build systems that can actually learn from information. It represented more probabilistic reasoning as opposed to specific rules. So how these evolved, and this will give you an idea of how artificial intelligence developed over time. Early in the 1950s to 70s, this is where the symbolists or the expert systems came in, and it saw huge breakthroughs in natural language processing. We even saw at this time the rise of the perceptron, which was an early neural network. By the 1980s or so, machine learning started emerging. And this is where Geoff Hinton's work started, and he emerges for many, many years. But then the AI winter came around 1990 and early 2000. There was less investment, less attention to AI because there weren't as many advancements within the field to even show what AI could do. And then data availability suddenly emerged. We had compute power costs coming down in the early 2000s. Cloud storage exploded, big data came with social media, and then there was explosion data that could be used for AI. And this is when neural networks saw the revival. By the year 2010 to today, we started seeing semblances of digital assistants through Siri, through Alexa. Generative systems started emerging much more broadly, computer vision, natural language processing, and now autonomous agents are happening. So the rules-based system, which actually started back in, I guess, 1950, 55 or so, these are one of the earliest approaches to AI. And they were simple, predefined rules to solve problems, to make decisions. The key points here were that these rules were based on expert knowledge. So there was an inference engine here. You'll see it in the middle. And very much like what the chatbot systems were today, this was the logic for applying rules. But these predefined rules made them rigid, made them really difficult to adapt to new situations. So as the complexity of the domains grew, the number of rules also needed to grow, and it started to run into scalability issues. So very simple examples. If a patient had a fever and a cough, difficulty breathing, then the patient may have pneumonia. In a warehouse setting where pick and pack robotic systems, if the rule states that if in location X at warehouse, the package is deemed ready, then pick up the package. Very simple rules. But the important thing is that within these rules engines, they were deterministic. That means where output is strictly predictable, repeatable for any input, the system operates entirely through these fixed rules. So there was no randomness and there was no probabilistic elements. One of the earliest examples of expert systems was Mycin. And it was an early expert system developed by Stanford. It was there to actually help doctors treat bacterial infection as well as blood infections. And they had about 500 to 600 production rules to emulate some of these decisions for infectious diseases. It interacted the same way like what the chatbots do today. There's a series of yes/no text questions. They had ranked diagnoses. There are reasoning explanations, and there was also recommendations on how to treat the patient. This was one of the earliest explanations of explainable AI, and they knew how important trust and explanation were needed within these systems. In around 1980s to 1990s, machine learning started to evolve. Instead of relying on these predefined rules, machine learning algorithms learn patterns and decisions based on data. So the ability to learn from data allows many of these machine learning systems to adapt and improve over time, making them much more flexible and powerful. This evolution allowed them to actually scale as new cases are introduced into the system. So I'm going to pass it off to Saurab to take you through the slide.
Awesome. Thanks, Hessie. All right, so let's start looking at like what the ML lifecycle is or what the machine learning lifecycle is, the big picture. So machine learning doesn't really begins with an algorithm or a model. It begins with a business goal. And let's just to make the idea concrete, let's take example of customer churn. How can a business identify customers who are likely to leave, and it can identify early enough so that it can take some proactive actions. Now, the first step is to define the problem. And like even for the same churn problem, we could frame it in different ways. Like, are we trying to predict whether a customer is going to churn in the next 30 days? Are we trying to rank the customers by the churn risk? Are we trying to estimate how much revenue is at risk? Or are we just trying to figure out like which customer is most likely to respond to a retention offer? Now, these framings might sound similar, but if you look closely, the first framing, like whether or not will the customer leave in the next n days, that will translate into a classification problem. The second question, like if you're trying to rank the customers by their churn risk, that will become a ranking problem. When we're trying to estimate the revenue of the risk, that becomes a regression problem. And if we're trying to identify which customer is most likely to respond to a retention offer, that's becomes a treatment effect or an optimization problem. So specifying the business problem precisely is, the first step and one of the very important steps, and primarily dictates what happens next. All right. So now that we have defined the problem, the next step is we collect and clean the data. So for let's say churn, collecting data might require figuring out, customer activity, product usage, support history, payment behavior, engagement, etc. Cleaning this data would mean like removing any duplicates that we have in the data. If there are any errors in the data, we get rid of them. If there are any nulls or missing values, we handle that. So all in all, making sure like the data that we have is trustworthy. Then the third step is featureization, converting this raw data into features, into numbers that the model can understand. So for one customer, those features, could be how frequently the customer uses the product, how many support tickets the customer has created, how long the customer has been with the company, etc. Then the next part comes where we select and train a model. The model is supposed to look at this data or the features that we have generated so far and try to identify the patterns. And mathematically, we can say that we want to come up with an equation such as y hat is equal to f of x. X is the customer, which is represented as features. F essentially is the model or the function that we're trying to figure out. And Y is what the model thinks about this customer. We then evaluate, tune the model, run them on unseen data, and running on unseen data is important because we don't want the model to just memorize the historical examples that it's seen, but we want the model to generalize well on new data. So when it sees a new customer, it should be able to make predictions more appropriately. And then finally, we deploy the model, we monitor it, and we also have to keep in mind that the customer behavior changes over time, the products change, the markets change, data changes. So machine learning essentially is not a one-time project. It's sort of a feedback loop where we make predictions, take some actions on that predictions, and monitor the outcomes, and then go back and keep improving. Now there are different type of machine learning models, algorithms, but you don't need to memorize each one of them. Most of the models have these three key ideas which can explain them. The first is representation. The model needs the world translated into numbers. Like, a customer becomes a vector of features. And when I say vector, like, I don't mean anything mysterious. It's a vector essentially is just an ordered list of numbers. A simple way to think about it is a vector is a row in a spreadsheet, right? So for example, like, a customer could be represented as like X, which is like usage, tickets, tenure, spend. So if one customer uses the product 80 times, let's say opens 3 support tickets, has been with us for 24 months, and let's say has spent some $10,000, that customer becomes a list of these numbers like 80, 3, 24, 10,000, and that's the vector. The columns in these spreadsheet with that will become the features, and every row actually which the customer is a vector. And when we club all of these rows together, that becomes the metrics. So that's the first big math idea. Machine learning needs real numbers. The real numbers needs to be translated into vectors. The second is probability. Now, most of the ML predictions, they're not certainties. They are like, let's say a churn model says this customer is going to leave. it's not saying that this customer is going to definitely leave. It is giving us a probability that this customer might have, let's say, 70% chance of leaving, looking at the data. The third pillar is optimization, or once we start looking at the data or the model starts observing the data, the model doesn't know what the underlying patterns are in the data. It makes some predictions, and then it compares the predictions to what actually happens. And then it compares or measures the error between the prediction and the actual. And once it calculates the error, it tries to figure out something which is called loss. And we'll look at what loss is in the next slides. But it calculates this loss, and then it changes its function a little bit so that this loss or this error gets reduced. And if we do this long enough, like with every example, if it tries to change itself a little, the hypothesis is that it'll come to a conclusion, or it'll come up with like a very good function f, which can mimic what happens in real life. So yeah, essentially three main concepts: representation, uncertainty, and optimization.
Machine learning has evolved through the 1980s, and so we're going to take you through three different types of machine learning. Supervised learning at a high level, it's a machine learning program. It's provided with training data that's already labeled. So the machine learns how to categorize example data based on previously labeled information. So it does require humans in the loop. Unsupervised learning, on the other hand, the machine has to learn from an unlabeled data set. So once you give a machine data points, it has to be able to interpret the information that it's given. Reinforcement learning, it learns by trial and error. And I give this example of Pavlov's dog. I don't know if people know who this famous psychiatrist, but he demonstrated in classical conditioning that when dogs learn to associate a neutral stimulus, which is a bell, with food, that triggers their salivation. So by repeatedly pairing a bell with food, Pavlov discovered that a conditioned response, which is the dog's drooling, could actually be created by the bell alone. So this was groundbreaking work that showed how behavior could be conditioned through association, and how this relates to computer programming. Computer programming learns by playing millions of games many times. When it makes a good move, we reward the program. When it loses, we don't give it any reward. Over time, it learns to maximize the reward without the human explicitly telling it the rules. So when we look at the different types of machine learning, we're going to take you through classification, regression. In unsupervised learning, we'll take you through clustering as well as dimensionality reduction, and we'll give you in some examples of reinforcement learning. So supervised learning, how it works. This is where the model learns from labeled data to predict an output for any unseen data. So the input feature is X, and it consists of training data that's pre-labeled that includes the color, it could include the size, it could also include the name that's categorized. The output Y is the unseen data that's yet to be predicted. So when you run the features through the machine learning algorithm, it means that the new input that's introduced, unseen, unlabeled data, will actually predict its label. This is a simple one. So classification is really about groupings. It's a binary qualitative value. Email is either spam or not spam. Online transactions are either fraud or not fraud. So the classification traits are that the output will be grouped into these discrete classes, and means that for future predictions, they can only fall within these target groups. This is one of the best examples of how supervised classification works. The idea of labeling is called data annotation. So CAPTCHA, I'm sure you all have heard of CAPTCHA. It's a security mechanism. They use it on websites to make sure that we can distinguish the difference between humans and automated software bots. So when CAPTCHAs are used to identify things like, let's say, traffic lights, crosswalks, in this case, muffins or motorcycles, they generate labeled data. The data is used to train the machine learning models, especially in supervised learning tasks. So Google has used CAPTCHA in its real world objects. So they use it to help to improve autonomous driving, even in their Waze as well as Google Street View. It will actually ask you if there's a car at the side of the road, if traffic is piling up, and it will ask you to validate that. So similarly, text-based CAPTCHA has been used to improve some of their OCR or optical character recognition systems, where you can help decipher distorted or scanned text. I'm sure you've seen a lot of that as well. So every time a user completes a CAPTCHA, they may unknowingly contribute to AI training, turning this huge security measure into really a large-scale human-powered annotation system.
All right. So like Hessie was already pointing out, classification actually is predicting a category, whether this transaction is fraud or not fraud. Is the customer going to churn or not churn? Is this email spam or not spam? How do we, actually add a category to a transaction or a customer? So how linear classifier does it is by creating something which we call a score. And the way to create calculate score is by this formula, like, B, something which looks like this, like B plus W1, X1, W2, X2. X's here are the features that we spoke about, and W's are the weights or the function that the model learns. So for this fraud example, the features could be things like if there's a new device, if the transaction was done from an unusual location, if it was done from late night, or whether or not this customer is a trusted customers. And the weights here, they tell us how much each of these signal matter. A positive weight essentially pushes the score towards fraud, and a negative score pushes the score away from the fraud. So like if a new device is added, that actually has a positive weight, same as unusual location. So these two signals tell us that, oh, okay, if you're doing it from a new device, if you're doing it from an unusual location, it's more likely that it's a fraud compared to trusted customer, which has a negative weight. So if it is a trusted customer, you know that it's less likely to be a fraud. The key point here is that, as he also pointed out in some early examples, we don't have fixed rules. What we have here is a formula or equation that we have come to learn looking at data, and the importance of it is basically derived not by some fixed rules, but by identifying the patterns in the data. So instead of a rule like, well, if amount is high and location is unusual, then this is a fraud, the model learns how much of each signal should matter based on whatever is the historical label data. Now maybe we can look at why this is called linear. Why is this called linear? So in this slide, we'll try to answer two questions. Firstly, why is it linear? And does linear mean like it's an overly simple model? So firstly, it's called linear because each change in the feature score actually changes the final score by a fixed amount. So for example, like if a new device changes from 0 to 1, the score changes or increases by 1.4. Same with trusted customer. If it changes from 0 to 1, the score decreases by 1. If the amount risk increases by 0.2, the score increases by 1.2 times of 0.2, which is 2.4. And in a two-dimensional space, a linear classifier actually looks like a straight line. In a three-dimensional space, like in the graph below, it could look like a plane, like the decision boundary or whatever linear classifier produces could look like a plane. And if there are like many dimensions, it could look something what you call a hyperplane. But the geometry essentially remains the same. On one side of the boundary, it's one class, and on the other side of the boundary, it's the other class.
I want to add one thing, just from a way of also explaining it. There is a direct correlation between X and Y on a plane. And so for marketers, we always think about, I always say the line of best fit. Anything that hovers around the plane or the line are those that are what we consider integral to the measure. Anything that falls outside of that plane is considered an anomaly. In many cases, they will not be considered relevant data. Does that make sense? Brian has a question.
Yeah, the question is, so this is, I'm keeping up barely, but it's all good. The question I have is basically, this is a lot of math around probability, right? Like clustering and probability starts to create answers in the end that AI would use. Is that sort of what's right? Like when I see all these dots, if you ever had a cluster of dots, that would be more true, would it not? Because there's okay.
Yeah,
like when they're scattered evenly, then it's all over the place. But if there's clusters, then that if you're getting back to your scenario, if we had a cluster about a certain target group to leave, then we would know they'd had a high propensity to leaving the
Exactly.
Okay, thank you.
Yeah, well, we'll go through that later, Brian, because that is actually under unsupervised learning. So you're actually ahead of the game.
Now we already looked at how a score is generated, but essentially a score is not a probability, right? Like score could be high, low, it could be negative. Probability needs to be between 0 and 1, right? So score itself is not something which is very easy to interpret. So in many classifiers, especially in linear classification, we convert the score into probability. And we use this formula here. We don't need to remember the formula, but the intuition is that it can take any number and convert into probability score which lies between 0 and 1. So like a score of 0 would translate into 50% probability. A score of 1 would map to 73%, 2 would go to 88%, and etc. Now, okay, well, we have a probability. How do we handle that? Like, what do we do with that? So now we need to convert this probability into a business decision. And that's where the thresholds come in. The business chooses the threshold, at what threshold above which we call this transaction fraud versus non-fraud. If we keep the threshold too low, we catch a lot of frauds, but we also flag or a lot of legitimate customers, and that can impact the customer sentiment. If we set the threshold very high, we reduce the false alarms, but now more fraud can go through. So for us to be able to make a decision like what should that good threshold be, should it be 0.5, should it be 0.88%, 50%, or 23%? For that, we need some metrics. And confusion matrix is one of the most common use metrics, or its most common use system to determine these thresholds. And in here, like if you look at it's essentially like a square where you look at different scenarios. The first one is like, okay, when the transaction was actually a fraud, and a model predicted fraud, that's a correct prediction. We call it true positive. If it was actually a fraud and the model did not predict it as false, we call it false negatives. It's a missed fraud. And then on the bottom line we have was actually not a fraud, and model calls it fraud. It's a false positive, false alarm. And if it was actually not a fraud and model also says that it's not a fraud, it's a true negative. And then again, looking at these numbers, we have to figure out like what's more important to business. Like, is customer sentiment more important? So then we want to reduce the number of false positives, or if having or missing a fraud is detrimental, then we want to reduce the number of false negatives. All right. So now the next question is like, how does the model try to learn better probabilities? And that brings us to loss. Okay. So loss is essentially, you can think about it as the model scorecard. It just doesn't tell whether or not the model is right or wrong. It actually also tries to measure how right or how wrong the model is. So for like classification problem, the model predicts a probability, and the actual label could be 1 or 0. In this example, 1 is fraud, 0 is not fraud, and the prediction pre is like what the model thinks, what's the probability of it being a fraud. Now, the good prediction essentially is something which should have a low loss. That's the basis. So like a transaction is actually a fraud, and the model predicted 95%, we should penalize it less. We were able to catch this. So the loss here would be low, like 0.05. But let's say if the transaction was fraud and the model didn't think that it was fraud, it's just 20% probability that it was a fraud, then we should give it a higher loss or penalize it even more. And similarly, in case of non-fraud, if it's non-fraud, but the model thinks it's a high fraud, then the loss should be higher or the penalization should be higher. So looking at these properties of loss or penalization, a function, a cross-entropy function came across, which can actually capture these things. And this cross-entropy function is what we primarily use in all sort of classification. Again, like the idea is not to memorize the formula, but the idea is to understand that, hey, we penalize more when there is a large divergence between what is predicted and what actually happened.
Just from a layman's perspective, I think the main thing with any model that's out there is that what this optimization is really just making sure that we minimize errors. So from what Saurab was saying, low loss means low error rate. So the better your prediction, you want to make sure you minimize any of those losses. And they keep going through this using different techniques through the model to ensure that you're always trying to minimize that error rate. Supervised learning regression. Okay, so this second type of supervised learning, we're using the example to actually predict housing prices. So it can be used on features like the size of a house, number of rooms, proximity to schools and churches. So the model is trained on historical data to learn the relationship that predicts the price of a house. So it learns from the relationship between the inputs and the outputs, and during the prediction, the model uses that learned relationship over time to estimate the target value for any of the new inputs. Okay, so I'm going to have Saurab explain how this is done.
To understand the maths behind regression, we'll take the running example of housing prices. So how do you predict what would be the price of the house? Again, a lot of concepts are very similar to what we were discussing in classification. We want to find a model which could be represented in this equation, y is equal to b plus w1 of size, w2 times bedrooms, w3 location. And the goal is to find these w's so that the predicted value of the house is as close to the actual value of the house as possible. So how we do it, again, we try and find the loss and we try to minimize that loss. So the loss here is essentially, squared sum of the differences between the actual predicted price versus the actual price versus the predicted price. One good thing about linear regression is that because the loss is in this format, it's squared and all, we actually get very elegant closed form solution. So what closed form solution is, we have one straight answer. So like in classification, we were discussing, we start something, we look at the loss and we update the weights, right, to minimize the loss. For regression, we don't need to do any of that. For regression, if we have all the data, we know there's only one value of these weights which will minimize the loss. So that we skip the part of iteratively finding the W's, and here by this equation, here we can accurately find the W's for ourselves. So does that mean that, if I have the data, I need to don't do anything else? No, there are, again, a lot of ways how you can improve the model. If you think that there's some scope to improve the model, and even with the best weights, we're not getting as close to the actual value as possible, we can try adding more features. Maybe for this particular example, we can see, does school district or the renovation status of the house impacts, makes the model give better predictions. Then we can transform some of these variables, like we can take like a log or age, a log of the size or the square of an age. The core idea behind it is like the size when a 200 square foot increase in the size of a 1,000 square foot house will have a lot more impact than the same 200 square foot increase in a 5,000 square foot house, right? If it's a linear size, we can't really capture that information. But if we take a log, then we would be able to capture that information. Then we can also add some interactions like, if it's the size of the house, like a 1,000 square foot house in downtown, which be much more valuable than a 1,000 square foot house in, let's say, a suburb. So adding that interaction can help model make better predictions. We have other more math heavy ways of improving the model, but maybe for time's sake, we'll discuss it later on. All right. Okay. So before we close the topic of regression, let's look at some other type of regression as well, which is called the tree-based regression. So linear regression, we've discussed, essentially assumes that there's a straight line relationship between the inputs and the targets. In the housing examples, there's like a straight line relationship between the square footage and the predicted price of the house. The decision tree regression thinks a little differently. It does not fit one smooth line. Instead, it splits the data into segments. So like, for example, a tree might first ask, is the home in a premium neighborhood? Yes. Then it might ask, is the square footage greater than 2,000? Yes. And then it might ask, was it recently renovated? And based on your answer, it traverses a path, and at the end of each path, the tree lands in a bucket, And the prediction usually is whatever is the average price of all the houses in that bucket. So mathematically, the decision tree is actually learning the split points that reduce the prediction error instead of one equation, which is valid for everybody. That's how decision trees work. But when do we choose which algorithm? So linear regression is great when we need more explainability. There's a strong baseline, and we need to capture a relationship which is reasonably simple. Decision trees are useful when the data naturally breaks into segments like, premium versus non-premium location, new versus old homes, high usage versus low usage customers. Trees are generally considered to be more expressive, but the problem is that the trees can actually overfit very fast. Like it can actually learn the underlying data or memorize the underlying data really fast. So it won't generalize very well to the examples that it hasn't seen.
Brian, you have a
Yes.
question.
Sorry. So data accuracy is really important for that, right? Because it kind of falls apart if you don't have all the little pieces to the math. Okay.
Mhm. Yeah, exactly. Like we discussed in the starting, data and clean up data, making sure that the data is trustworthy is very important because the model is learning patterns, looking at the data. So if there's anything,
it's very linear, it's very direct, right? So you have to make sure that all the inputs are accurate to get an accurate output. Okay, thank you.
Okay. We're going to the second part of machine learning. This is unsupervised learning. And Brian, this speaks to your stuff on clustering earlier. So this means we're not actually giving the model labels like fraud or not fraud or actual housing prices. In fact, what we're trying to do is we're asking the model to find the structure in the data it's given. So in this example, we're clustering customers. One group may look like city dwellers. All these people within the green, we notice that they have similar traits. They're city dwellers, single moms, household income 70K, average 2 kids, etc. So the model is not told these names. The model only sees the data points and they interpret a lot of the clusters afterwards. So as we see here, it's great for customer segmentation. It's great for targeted marketing and product recommendations. The caution here is that it doesn't mean that clustering, again, is an absolute truth. It discovers a similarity of all the features that we give it. So we can cluster by income, location, family size. We may get a different demographic segment. If we actually group things by, let's say, product usage, purchase frequency, engagement, we may get an actual behavioral segment, which is very different than what we're seeing today. So the business question is the thing that's going to determine the features that we're going to be using to determine the clusters that actually materialize. So to understand the math behind it, I'm going to go back to Saurab to show you how clustering is measured.
Like as you mentioned, in clustering, we convert all of these customers or whatever we're trying to measure into points, and then you try to group similar points together. Bring the close points together and call them a cluster. All right. So how do we do that? We can, like, the only way we can do it, if we have some idea of distance between, then only we can say, oh well, these 2 points are close together and these 2 points are far apart. There are multiple ways of defining distance, calculating distance, but on this slide, we talk about like the top 4. These are like the ones which are most generally used. The first one is the Euclidean distance. So it's the straight line distance between any 2 points. We have a customer into this high dimensional space. We calculate how far apart these 2 points are, and that's our Euclidean distance. It's very simple, very intuitive, but it has one problem, that it's very sensitive to scale. So let's say we have 2 dimensions. One is for income, and one is like how many times the customer visited a page. And now the income, let's say it ranges from 0 to 200,000, but the visits, or how many times the customer has looked at, come to the website, it just changes from 0 to 10. So naturally, you'll believe that if 2 people have same income, because the value of the income is so high, the distance between them will always be shorter, irrespective of how common their tendency is to visit the websites. So that's one of the problems with Euclidean. Then the next sort of metrics which came, distance metrics, which came, was the Manhattan distance. Manhattan distance, it measures the grid-like movement across dimensions. It doesn't go on a straight line, but it moves one step top and then one step left until I reach the next point. This again was a little bit of improvement on Euclidean, but it still suffers the same problem. Like if income is very high, if one of the dimension is, the values are very high, it will always take longer for one point to reach the other point. Third one is the cosine similarity. Now the cosine similarity actually fixes the problem scale because it doesn't calculate point distance between the 2 points. It calculates the angle between the 2 points. And this is very useful, very commonly used in text, embeddings, behavior vectors, where the patterns matter more than the absolute sizes. So like, if you have two users who have similar preferences, both of them buy same kind of stuff, like both of them are buying home improvement stuff, then how frequently they buy or how many products they buy, it doesn't matter because the angle between them will remain the same. It's just like one point would be farther up and the other point would be a little below, but the angle from them will be really close. And then the fourth is Jacquard. So it's a little different from the first three, but Jacquard I wanted to mention because Jacquard is something which is used to find differences or similarities between two clusters. So let's say, we have our data and we found like 5-6 clusters and we see that, oh, this cluster is really nice. I want to find more clusters which are similar to this one. In that scenario, you'll use Jacquard similarity. You look at two sets, you look at what are the points which are common, and then we divide it by the entire space. Then it comes to, now that we have idea of metrics, we'll just go over one of the key algorithms for clustering. The first one is k-means clustering. It's like a center-based clustering. What we do is beforehand, we choose what is the number of clusters that we want in the data. And the algorithm tries to find or group these customers or these points into these clusters. Each point, how we begin is like we start with assigning each point to its nearest center. Then we try to see like how close these points pack together. And based on that, we change the center a little and then reassign the points to the nearest cluster again. And if we do it long enough, we would find these really very well documented clusters. This is very widely used, it's very easy to interpret. The only downside is that you have to choose the k beforehand. And this algorithm tends to struggle a little bit with odd-shaped clusters. So the reason why it suffers with odd-shaped clusters is it doesn't have an inbuilt mechanism of avoiding anomalies or noise in the data. Then comes dbScan. dbScan is density-based. So it tries to find similarity. It looks at, oh, which areas in this 2D space have a large density of points. And it calls those as clusters. So you see, if k-means tries to fit every point into a cluster, and dbScan says like, oh, if there's a high density of points, I'll call that a cluster. And if there's some points which are like, these x's lying around, I'll just consider that anomalies and I will not, care about that at all. And then there is a third kind of clustering, which is the hierarchical clustering. So hierarchical clustering, essentially what it does, it takes points and it starts combining the points based on some properties. And eventually when we have like enough points linked together or enough number of clusters already formed by the linkages, we basically terminate the algorithm. The benefit of hierarchical clustering is that not only you get like similar points together, but you also get to see the relationship between these 2 points. And location analogy would be a better way of understanding, like each house address is a point. Then, you start combining points which are in the same zip code together. Then you start combining zip codes into a common county together and so on and so forth. And you stop where you feel like, okay, now I have enough clusters to work with. I don't want any further. The only downside of hierarchical clustering is like it's very expensive. So if you have too many data points, it's going to take you forever to get that.
Natalie, do you have a question?
Can you go back one slide?
Yes. This one?
So I kind of missed how this clustering is related to the clustering on the next slide.
Okay. So the way we can define clusters is we want to find points and we want to group the points which are close together into a same cluster. So we need to figure out what is closeness. How do we say this? Oh, these 2 points are close together. We need to define a matrix, and that's the distance matrix. So this slide talks about what the distance matrix is. So Let's say in k-means clustering, we'll calculate the Euclidean distance between points, and the points which have fewer or smaller Euclidean distance, that become a cluster. Does
And then
that
we
explain?
can cluster those Euclidean points by either K, dB, or hierarchical.
Yeah. Very
So
good
the
point.
first one's kind of like the how we're going to measure the distance, and the second one is
Yes.
how we put the clusters together.
Yes,
Okay.
that makes sense.
Thank you.
Okay, Barry?
I just want to know under DB scan, what happens when it's a happy face?
Yeah. So this is one good property of DB scan, because we can get rid of, like, we can think that some of the points are anomalies. So you can come up with some odd shaped, like smiley face, grumpy face, and all. K-means, because it tries to find a center and then pull all the points towards that center. You'll mostly get what's called like a circular shaped clusters. That's one of the benefits of DB scan.
So we're going to get into, Anand, yes?
Sorry, just one quick question. So all of these points over here are essentially the features that we are, like, for example, it could be a customer, or it could be, I don't know, a house, and then we are trying to compare both of those, right?
Yeah. You can think of it as customer. So like every point is a customer, and the x-axis could be one of the feature of customer, like transaction history or income, and the other feature, or the y-axis could be another feature, which is like how frequently the customer moves around.
Got it. Thank you.
So the other part of unsupervised learning is dimensionality reduction. So this is the process. If you look at on the left-hand side, it's a process of actually reducing the number of inputs in a feature in a data set while ensuring the most important ones are preserved. Most data scientists do this because the goal is to minimize the loss of the value of the data and retain only the important stuff, throw away any stuff that's irrelevant. They do this to also try to, let's say from a computing perspective, if it takes long to actually compute because there are too many features, then it's a way to create efficiencies. But I'll show you an example. So here we have a flower, and it has 400 dimensions. It could be the petal width, the type of color, the depth, the sepal length, all that stuff, the texture, the height. If you reduce, let's say, these 400 dimensions down by 10x, you could still see in this picture that you still could identify that flower. If you reduced it by another 16x to 25 dimensions, you'd still be able to identify the flower, even though it was a little bit murky, right? And the last example, if you reduce the dimensions too much, you wouldn't even be able to identify the image. So the reason for dimensionality reduction, again, is how many times can you reduce it to be able to ensure that you're only keeping the features that are valuable.
Awesome. Yeah. So maybe we continue the example Hessie was talking about, that you have like this flower, and you can keep changing the opacity, making it smaller, compact in size, and that basically is required, or like that how much opacity or how much we can reduce the dimension is primarily based on like what problem we're trying to solve, right? So like if you want to figure out, what, I just want to know if what type of flower it is. Then we can reduce the opacity to very small levels, and we can still keep all the information available in the image to make the right prediction. But let's say if we are trying to count the number of leaves in the picture, then probably need it to be at a higher resolution or higher dimensions, because we need more important data points. And that's basically what entire math about dimensionality reduction is. A customer could have like 100 of features. The dimensionality reduction is like, hey, can we represent this customer with fewer dimensions while keeping all the important information available? Again, like it's sort of a trade-off. There's no, if you reduce the dimensions, you're definitely going to lose information. So the key is, how do we reduce the dimensions without losing information? And it depends again on like what the problem that you're trying to solve. Fewer dimensions are easily simpler, faster to understand, easier for the models to work with. But yeah, they'll start losing information. So depending upon how complex task you're trying to provide, you will want to see how much dimensionality reduction you want to do. PCA is like one of the ways how we do dimensionality reduction. That's like principal component analysis. And the basic or the high level idea is, let's say if you have a customer and all your customers have, login from non-suspected locations, or all your customers have, let's say, 10,000 income. Because there's no variation in there, that particular feature doesn't add that much value. So you can actually remove that feature and still have enough information to make classifications. So that's essentially what PCA is. It tries to find which dimension has the highest variation in the data, tries to keep that while removing the dimensions which do not have enough variation, right? So that's basically the idea of PCA and how we do dimensionality reduction.
I'm just looking at the clock, so I just want to make sure that we're getting all the information here. So with reinforcement learning, this is by trial and error. Within this system, there are four main components. You'll have an agent, you'll have an interactive environment, and there's an algorithm that will steer the action taken by the agent. And then there's going to be this feedback mechanism to actually reward and penalize the agent as per the action. I'll let Saurab take you through.
Okay, yeah.
Maybe you can go through the example.
Yeah, exactly.
Just high level this one.
100%. Yeah. So the reinforcement learning is if this is the current state of our actor, what action should we take so as we maximize our gains? And it's all the maths, some formula which you guys can look later on. But let's walk through an example, and that might help us understand. Okay, so let's say current state, we have a customer who's visiting our pricing page. He has visited twice but have not purchased. Now we have two options, two things that we can do. One thing is that, okay, let's offer him a discount. And second thing is, okay, let's wait, let's see if the customer is really interested, and not do anything and see, if he comes back and actually takes a purchase. Then we have to calculate, okay, what is the reward of each actions? Like, let's say we do end up sending a discount and the customer actually purchased the product. So now we have to calculate what was the reward, or how much value did that generate for us. So let's say the price was $10, the discount was $3. So we calculate the amount, or the reward for us was like $7. Okay. Then with this $7, we try to estimate what would be the future rewards. Let's say, now that the customer has actually taken our product, he's going to probably move onboarding part. And the model tries to look ahead and sees like, okay, given if the customer purchases the product, how much more value can the customer generate? And it looks at all different actions that could be provided next, and it picks the maximum value that would, that would be generalized. And then it updates the value. It updates what is the maximum benefit which we can get from the customer. And in this particular case, let's say it comes to 11.5. Once it comes to 11.5, we go back, and what our initial assumption was that, if we send a discount, we would totally generate some value of $6. We have to now update it because actually the generated revenue was 11.5. So you see, it's sort of an action-based thing which we are learning in real life. We have some hypothesis that, if we send a discount to the customer, we'll make $6. But when we actually send it, we see that, we can actually realize $11. So we go and update our assumption. And if we do it against a lot of interactions, we can actually come up with like a realistic estimate of what is the potential value of each action. And that's basically what drives businesses.
So we've come to the end of machine learning. And so what we've demonstrated so far is a glimpse of what we've been able to achieve through this technology over time. Just to give you an example of what has actually transpired from these systems, we've been able to build amazing recommender systems. Understanding customer has never been more important than now because of these systems. We can identify fraud detection, diagnostics, and computer vision has really allowed us to properly classify things even to the tiniest pixel. Market forecasting, weather forecasting, and we're just getting started. So I'm going to take you through, like, the next part is neural networks. So For more than 30 years, Geoff Hinton actually hovered around the edges of artificial intelligence research, but he clung to a specific proposition that said that computers could think like humans do, and they could use intuition rather than rules. So today, there are scientists around the world who are being hired to actually pursue some of these technological answers to some of the biggest problems. How can AI be used to diagnose cancer in children? How can you detect dementia in speech? How can we build machines to help humans to even see as well as animals? I pulled up this quote because this is one statement that's fairly profound from how he's actually built these systems. And he said, "We're machines. We're just produced biologically. Most people doing AI don't have a doubt that we're machines. We're just extremely fancy machines." And I shouldn't just say just, we're special, wonderful machines. Let's look at how humans process information, why it's pretty fascinating to see how AIs can replicate this. This is called a neuron, and they're also called nerve cells. So they're the fundamental units of the brain and the nervous system. More than that, their interactions define who we are as people. So they're specialized cells within our nervous system. They have a sensing, like the internal as well as external stimuli, and they process information. So the tentacles that you see here are the synapses. They fire and transmit signals throughout the body and to other neurons, and they direct muscle action, which is actually the output. So imagine replicating the actions of a biological neuron through computers. So these are the nodes and edges of a neuron. Each node represents the information that fires off signals to other networks. The edges here are the synapses that process the information across the network, and they go at unimaginable speeds, and they activate signals to other neurons. The brain actually consists of over 1 billion neurons. Each neuron forms about 1,000 connections to other neurons, resulting in, what do we say, 1 trillion connections overall. If each neuron could actually store a single memory, running out of space would be a problem. So, but what neurons do is they combine so that each one helps the memories all at once. They exponentially increase the brain's memory storage capacity to around, let's say, 2.5 petabytes, which is about 1 million gigabytes. So if we were to translate this, 2.5 petabytes would be enough to hold 3 million hours of TV. So you would have to leave the TV running continuously for more than 300 years to use up all that storage. So we have this amazing capacity within the human brain already. Geoff Hinton immediately understood that the human brain worked like that too. Information in our brains is spread across a vast network of all these cells that are linked by this endless map of neurons that are firing and connecting all these different paths. And so the computer could work the same way. It receives input data, it decides for itself what features are relevant, and then the deep neural network analyzes using these learned representations, much like how a person approaches a problem. In these networks, there are way more parameters. So there's so many more knobs that need to be tuned within this neural network. And they process it through what we call these hidden layers. And advanced computation statistics are performed here to produce an output here, to understand the relationships between these different nodes. So they process it through the different hidden layers and they produce an output. Deep learning networks will often improve the more that you increase the amount of data. So within the output layer, it will produce a weight, and then it will go back to update any new inputs that come in here to actually determine what the new weights will be. And the strength of the connections over time eventually become what your model will be. Saurab, you can take this one.
Yeah, so essentially the simple neural networks, if you see, this translates or looks roughly like what we were discussing in classification or what we were discussing in the linear regression part, where you have inputs and you have some weights, which is the middle layer, W, and then we get some outputs, which was Y. But what deep neural network changes is we have inputs and then we have stack of these weights or a stack of these functions. So instead of one function, now we have like multiple functions which could be stacked together. And the idea is that once we have all of this stacking, we can actually understand far more complex patterns within the data than what a single equation could have done.
There's a question, Natalie?
Sorry, just to go back to that again. Sorry, the hidden layers are the structured and unstructured.
Yeah. You can think of the hidden layers. So yeah, you remember when we were discussing about linear regression or linear classification, we were talking about W's like W1, W2, etc., etc.
Mhm.
So these yellow dots, you can think of them as W's. These are like the W's which interact with your red dots, which are X's. In linear, we only had one set of W's, but in deep networks, we can have multiple W's. And the
So
idea
your
is that,
W's, are your W's your weights?
yes, the weights, yes.
So and the weights are relative, Natalie, based on the data, and all the weights always get updated depending where the signal is coming from. If it's coming from 3 nodes, then that weight may change. And the weights change based on the influence of each of the nodes, right? And so if you're, let's say, a weight that you're a node that doesn't get fired at a lot, then your weight stays at 0. But depending on where the signal comes from, your weight may change. And at the end of it, the relative importance of each of those weights will determine what the output is going to be.
Picture kind of shows that all the yellows are equally weighted, but in reality, they would have more lines, less lines, shaped
Yes.
differently, and that's
Yes.
what becomes
Yeah.
the output. Yeah.
That's
Okay.
right. We'll take you through an example so you understand. Okay. For this, I used a marketing example. Okay. So this is a simplified explanation how these predictions work. And I'm not going to go through all the deep layers. I'll try to take you through a sequential layer, but you'll understand how deep learning actually works. So imagine you're a publication and you want to acquire Jennifer as a customer. You want to understand the likelihood that she will register for your magazine, but you want to ensure you also retain her as a customer. So what key traits can we leverage to improve the probability that she is going to actually register for your magazine? So there are many more dimensions, as I indicated, but we'll go through something that is more of a customer journey, a sequence of events. She clicks on an ad. She visits a website, chatted with sales, but all these lead to a conversion, which is registration, right? So how do we value all these events? And then after she registers, becomes a customer, then there are other actions like downloads an app, customer service, customer review. These are all retention type metrics. So in this time series, these mapped events are put into chronological order of a customer journey. For a given customer journey, each of these features will have a different weighting based on how important that feature is to the overall contribution. The challenge is that each step of the customer journey isn't linear. It's going to be different for everybody. So somebody could click on a website, register for a subscription, and then they actually can churn. They may not do any of these things. Another customer may actually click on an ad, visit the website, but never register at all, and they can fall off here. So there are so many different paths to either becoming a customer or even moving away from being a customer later on. So the sequence is going to be common to all the customers, and they may behave differently. These artificial neural nets, they actually calculate the probability of each of these features as it relates to the outcome of registration. So I'll show you how this looks like. So for the ideal person, we're creating a model. We use the training data to find similar people like Jennifer to determine what the base model is going to look like. So for right now, the percentages are clicked on an ad right now, 12%. Website visit, 18%. That's the attribution to what they provide to the overall registration process. So the likelihood of this, the higher it is, means that it is more influential to someone actually registering. One thing we also need to take in consideration is what happens after she registered and what are the relative weights that each of these events have to keeping her as a customer. So this will determine whether or not only if she registers, but whether or not we can retain her as a customer. Once we have our base model, we start to bring in more customers to determine how the model changes, right? How did the website visits actually contribute to the overall contribution to the conversion, which is the registration? We run this sequence almost 1,000 times more with new customers, new acquisitions, to determine how each of these model weights change the model. And we will determine which features will become much more influential as more customers are bringing in. And then what we'll start to see is that the model itself will continually improve and it will become a lot more predictive. Okay, does that make sense to people? Yeah.
So the model is tuning itself, right? It's constantly getting sharper and it's going to school in a way, right? Like to learn.
That's right. That's right. And then over time, let's say if you did a promotion that was trying to mitigate customer churn, then you may actually come up with new features that, let's say if you're A/B testing like you marketers always do, you may test 4 or 5 new features to determine whether or not that actually has a bearing on mitigating customer churn. And then you could add it back to this model as new features. Okay. So at the end of the day, it's really all about patterns. Machine learning is about creating algorithms that learn complex functions or patterns from the data, and then they make predictions on it.
This line is pretty much the continuation of what we were discussing earlier, what Natalie asked. Linear model is one equation, neural network is essentially multiple equations plugged in together, and the job of each equation is to learn something different or learn something new. All right, so maybe on the next slide, one thing which neural network, or which basically made the biggest impact in neural network, is that the introduction of nonlinearity. So now we're no longer just looking at the linear equations. We add some nonlinearity, and what that allows is now this function, which was essentially before like a linear line, straight line, then in precision trees, now it doesn't have to be straight, it can curve, but within each segment, it still has to be straight. So like, it's a horizontal and vertical line. So it's a combination of horizontal and vertical lines. And there's only as much you can convey with this kind of stacking things together. What neural network does is adds the nonlinearity, or which allows it to change the straight lines into curves. And now that you have multiple curves, you can stack those curves together, and then you can do any sort of classification or do very complex classification together, which previously with previous models was not feasible. So here, this is the same example of housing prices. So the dots are actually the prices depending upon square footage. And you see that on the top, there's a slight dip. This linear line can never figure that part out. If you try to capture the dip, you'll miss out on what's in the bottom half of the prices in the bottom half of the chart. Decision trees, you can do slightly better, but as you see, it's still like straight horizontal lines. So it can do a better job than linear classifiers, but it will still not be able to capture everything. But the neural network, as you can see, now there is the ability to change this linear or straight lines into curves. And now you can pretty much model not everything, but very complex relationships. This is just like one of the fundamental changes which happened with neural networks, is because we stack stuff together, the lower layers trying to learn simple features, the layers above that try to combine those simple features into something, and then the topmost layer try to learn the abstract patterns. For images, the lower layers might learn the edges. The layers sitting on top of the edges could actually combine those edges and try to understand, oh, what shapes are in this image. And then the even higher layers can combine these shapes and try to see, oh, what the objects are in this. So like edges can translate into eyes, nose, whiskers, and these shapes can combine to tell that this is actually a cat because it has eyes, nose, whiskers, etc. And the same things goes for, like, let's say, customer example, where the lower layers can understand events, and then the higher layers can combine that events and understand a behavioral pattern, and then these behavioral patterns can combine and tell the model what is the churn risk of this particular customer.
And so finally, we'll get into general purpose models. And this is what everybody in the world is using today. And so we're going to go through some just quick definitions so people understand the differences. Generative AI is really just your creative tool. It's an umbrella term that basically means that these LLMs have the ability to create text, code, images. It understands the space and can generate novel content, but it still waits for human instruction. The LLM is just that. It's a brain, but it doesn't really do anything. It has no memory, it has no intent. It is the base model that predicts tokens based on the patterns in the data, just based on input and output. So it requires an interface like generative AI in order to do that. AI agents and agentic AI are two totally different things. AI agents are the workers, so they execute predefined tasks. They detect intent. You can call tools like APIs to handle specific responses. So think of them as handling one task at a time. By the time you get to agentic AI, this operates within goals, within plans, within huge context and memories. So think of it as agents and sub-agents. They monitor progress. They decide what to do in real time. Without real human instruction, they can have human direction, but they don't have specific instruction. So where we've got to today is a progression of features. It shifts away from prediction now to real orchestration. And we moved away from commands. Now we're moving more towards autonomy, as you all know. So some of the key traits of generative AI right now, they're still inherited a lot of the deep learning systems like from Geoff Hinton. There is no new technology within generative AI, which is the reason why even within these deep learning layers, it's still very much opaque. It learns from massive data sets to generate new image and that new images and new text, which is very new from the last version of AI. It's trained on internet data, but we actually don't know what the training sets were. It still needs a lot of human feedback, but it's limited because a lot of the reinforcement learning for human feedback hasn't been easily available. And this can cause harm because of that. So it will always have probabilistic outputs. It can lead to hallucinations because of that. It still has a fundamental barrier in that it doesn't really understand yet. It doesn't really reason. And so it's still prone to aberrant behaviors, and it's very costly. So the key differences here, nothing happens at the LLM level. This is the trained model. Generative AI, it focuses on content creation. It's still very narrow task-oriented. AI agents use various searches, API, one agent. Typically, it's repetitive. Agentic AI is more open, high-level goals, many agents, multiple tasks. Okay, and the relationship, just to dumb it down, generative AI creates and drafts an email. AI agent sends the email. Agentic AI identifies a client. It schedules it, sends an email, handles the flow without the human input. So where we are today, for a long time, advancements across the evolution of AI have been in narrow AI. That's where we are today. It's human controlled, human oversight. Over the last 3 years, we've moved into general purpose systems. There's still kinks in that process, but the intention is to really generalize knowledge from one domain to another. We're not there yet. And as for superintelligence, forget about that. Until we get to AGI, we really don't know whether or not we can get to ASI, probably after I've passed. So for now, we're squarely within the advanced machine learning phase. the rate of scale storage models that can contextualize and learn at greater speeds is what we're trying to get to. But we need oversight, we need remediation, we need token costs to come down quite reasonably. And we have to also question whether or not the power that we're using is going to be the panacea for energy consumption. So we still have a ways to go to get to AGI, but the implications of getting there are still being debated. That concludes our presentation. I know it's a lot. Feel free to reach out to either Saurab or myself if you have any questions. We'd be happy to help.